If you've ever floated on an ocean swell, you'll know that the sea moves constantly. Zoom out and you'll see the larger picture. Our Earth, covered by 71% water, moving in one enormous current around the planet. This intimidating global conveyor belt has many complicated drivers, but behind it all is a simple pump that moves water all over the Earth. The process is called thermohaline circulation, and it's driven by a basic concept, the concentration gradient. Let's leave the ocean for one moment and imagine we're in an empty room with lots of Roombas sardined together in one corner. Turn them all on at once, and the machines glide outwards, bumping into and away from each other, until the room is filled with an evenly spaced distribution. The machines have moved randomly towards equilibrium, a place where the concentration of a substance is equally spread out. That's what happens along a concentration gradient, as substances shift passively from a high or squashed concentration to a lower, more comfortable one. How does this relate to ocean currents and thermohaline circulation? Thermo means temperature, and haline means salt, because in the real-world scenario of the sea, temperature and salinity drive the shift from high to low concentrations. Let's put you back in the ocean to see how this works. Snap, you're transformed into a molecule of surface water off the temperate coast of New York, surrounded by a zillion rowdy others. Here, the sun's rays act as an energizer that set you and the other water molecules jostling about, bouncing off each other like the Roombas did. The more you spread out, the less concentrated the water molecules at the surface become. Through this passive motion, you move from a high to a lower concentration. Let's suspend the laws of physics for a moment and pretend that your molecular self can plunge deep down into the water column. In these colder depths, the comparative lack of solar warmth makes water molecules sluggish, meaning they can sit quite still at high concentrations. No jostling here. But seeking relief from the cramped conditions they're in, they soon start moving upwards towards the roomier situation at the surface. This is how temperature drives a shift of water molecules from high to low concentrations, towards equilibrium. But seawater is made up of more than just H2O. There are a great deal of salt ions in it as well. And like you, these guys have a similar desire for spacious real estate. As the sun warms the sea, some of your fellow water molecules evaporate from the surface, increasing the ratio of salt to H2O. The crowded salt ions left behind notice that lower down, salt molecules seem to be enjoying more space. And so an invasion begins, as they too move downwards in the water column. In the polar regions, we see how this small local process affects global movement. In the Arctic and Antarctic, where ice slabs decorate the water's surface, there's little temperature difference between surface and deeper waters. It's all pretty cold. But salinity differs, and in this scenario, that's what triggers the action. Here, the sun's rays melt surface ice, depositing a load of new water molecules into the sea. That not only increases the proximity between you and other water molecules, leaving you vying for space again, but it also conversely dilutes the concentration of salt ions. So down you go, riding along the concentration gradient towards more comfortable conditions. For salt ions, however, their lower concentration at the surface acts like an advertisement to the clamoring masses of salt molecules below, who begin their ascent. In both temperate and polar regions, this passive motion along a concentration gradient can get a current going. And that is the starting point of the global conveyor called thermohaline circulation. This is how a simple concept becomes the mechanism underlying one of the largest and most important systems on our planet. And if you look around, you'll see it happening everywhere. Turn on a light and it's there. Concentration gradients govern the flow of electricity, allowing electrons squashed together in one space to travel to an area of lower concentration when a channel is opened, which you do by flipping a switch. Right now, in fact, there's some gradient action going on inside you as you breathe air into your lungs, letting the concentrated oxygen in that air move passively out of your lungs and into your bloodstream. We know that the world is filled with complex physical problems, but sometimes the first step towards understanding them can be simple. So when you confront the magnitude of the ocean's currents, or have to figure out how electricity works, remember not to panic. Understanding can be as simple as flipping a switch.